Okay, so we'll start here with the project. We have the project criteria that has been uploaded already this afternoon. I have the design criteria. It refers to a 3-story office building. So I guess we know what does it mean by an office building. It means the life load is going to be 50 PSF reduced according to the CBC. And also you're going to have the 15 PSF for the partitions. And of course, you're going to be treating it as life load. The proposed story height is 14 feet, which means from one floor to another floor. And of course, we're going to be using the CBC 2019. I'm going to say here the scope of work. What do you need to do? We're going to have certain sections and submittals that you're going to be seeing very soon. Here's, for example, the first submittal. And each submittal is going to show exactly what is needed for it. And this is going to be in lieu of the homework. So whenever I have one of these, most likely I'm going to be canceling the homework that goes with it. So you don't have to worry about the scope of work because the scope of work is going to be detailed for each submittal. For now, we have only one submittal assigned to us. For the material properties, the steel beams and columns is going to be grade 50 ASTM A992. For the metal deck, it's going to be W3 Verco metal deck, and you have the catalog, you have all the information, you have seen it. When we come to the weight and the concrete topping, it's going to be 3¼ inch lightweight concrete topping. F prime C is going to be 3000 psi. Therefore, the total thickness of the slab is going to be 6¼ Okay. For the load criteria, this should have been the 2019. In chapter 16, it has a life load on occupancy, and of course you have the partitions. Let me just correct this. We have the exterior skin, which is 20 PSF of the exterior elevation. Let me show you exactly what we are talking about. First, let's look at the plan, try to understand it, and see what's going on there. Here's a plan view. We have a bunch of grid lines running in the, I'm going to say this is giving the north-south, and this is giving the east-west. Reason is because if you look here at this symbol, this is giving the north direction. So north is giving this way. So this give you the grid lines in the north-south, and this give you the grid line in the east-west. Let me zoom in and let's see what beam size do we have. It says here, here's a beam size W21 by 44. This is a beam size here. For the span of this beam, you can just add these two numbers from here between grid lines. And then it says here, camber of 1½ inch. Camber is the opposite of the deflection. So if you like to, let's say, work on the deflection because deflection of the beam is not working, what you can do here is to provide some camber. So camber means to bend the beam during fabrication, you bend it upwards. So when you add the whole dead load, the beam is going to be almost flat. So this here gives me an idea that dead load deflection for this steel beam is about 1½ inch, maybe 2 inches, something in this range. And for each separate beam, I can assign the camber, but I would rather try to make it as uniform as possible. So here, if the deflection had been, let's say, 1½ inch due to dead load only, you're going to place this camber, and the camber is going to be also 1½ inch. So once you pour the concrete and the concrete is going to be hardened, this beam is going to be flat. So the only check you're going to be doing in this case is going to be the problem, or the check that you really need to do is going to be the live load deflection. Why? Because we have taken care of the dead load deflection. When you see here the word here do, it means this is going to be the same between two beams of the same size. So here, for example, it says W2144, C 1½ inch, same size between them, and instead of repeating this, we just say do, which is the repeated, just repeated. Same thing here. Between here to here is going to be the same beam size. Look at this beam size for the span of 29 feet and 8 inches. it is W16 by 31. This one, this is what we call here grid line R and Q. We have also Q and P, or P and Q. Q and P is going to be 24 feet plus 9 feet. How many feet we're talking here about for the span? It's going to be 33 feet from here to there. The beam size W16 by 31 has a camber of 1 inch. And then it says here do all the way to the end. The standard that we're doing here, that we're going to be providing a stud per foot, just one stud per foot. Unless we come here and then we put number of studs in a box like this, which means here I need to add 45 studs from that point to this point. Otherwise, it's going to be 1 per foot, meaning from here to here, I have here 3 studs. But in here I have 45. And the reason is because this beam is a special, it's kind of a special. It is used as drag beam because I have some lateral force resisting element here. I don't want to concentrate on the seismic drags and this kind of things, but what I care about is going to be the beam design and the camber. This is going to be W16 by 31. The span is 33 feet. I know the tributary width, which is 28 feet and 3 inches, divided by 3 to have the spacing, right? And this is going to be the tributary width for each beam, so that you're going to be able to work on the life load reduction. Can I bring here the first submittal so that you can start to work on it, start from today. It says develop the load criteria for the floor design. Load criteria means determine the dead load and life load. And at the end, you're going to have the design load. So design load meaning what? Design load means W ultimate. You're going to be doing this once for the floor and once for the roof. And here's the difference between these two. It says here for the floor design, and certainly for the floor design, you're going to be doing what? 50 PSF and 15 PSF for partitions. For the roof, it's going to be only 20 PSF. And to reduce the life load, you cannot really use the method that I used. There's another method in the code. So what I want you to do is to go to the roof design in the code and look at the way that you can reduce the life load from 20 PSF for any roof to some other number. So I'm going to say here, roof life load usually. So I'm going to say life load for the roof, 20 PSF. But you still need to reduce it based on the tributary area for each one of these beams. So when you do here the load criteria, you don't know exactly which beam that you're doing it for. So in this case, you cannot really do the reduction here because you didn't work yet on any of the beams. Because I simply can put this plan here for you and then look at this beam. I'm going to say here tributary width for this beam is going to be, let's say, about 9 feet multiplied by 29.8. But for this beam, it's going to be 33 feet multiplied by the same width. So each one of these beams may have different life load in the design of it. So I'm going to confirm this again. And here, you don't really need to do any reduction in the first 2 steps. Are we good? Are you guys following me?
Sir, can you repeat the point about studs?
What?
Can you please repeat the point about studs? How many studs we have to put?
I'm not there yet at the studs. I'm still working here on the load criteria. I'm not there at the studs yet. The studs is going to be a discussion. You mean the Nelson studs, am I correct?
Yes, sir. You said that we have to put one every 3 feet.
No. I was talking here about the tributary width. And what I was saying in the tributary width for the beam is going to be equal to, which means the spacing between each beam and the other is going to be 28 feet and 3 inches divided by 3.
No, sir. When you said that the number of studs will either be given in the box, otherwise we'll take it one per foot.
Yeah, that was like
that point. Can you please re-explain that point?
Okay. I was saying that minimum number of studs, if you didn't see it here, is going to be a stud per foot, and that's it. And then we finished this issue about the studs after we went through this plan view. And then after this, I start to see here what is needed in this submittal. So the first two items that you need in this submittal is going to be about the design load. This is what we call here load criteria. Are you following me or
Yes,
no?
sir.
Okay, good.
Yes, sir.
So let's stay here. Let's not go to the studs now. All right?
Okay.
So what I was saying is life load reduction doesn't need to be included in item 1 and 2. Items 1 and 2 does not include any life load reduction. The reason is because this is generic. This is general here for any beam. But if you like to reduce the life load, you need to go to the tributary area that you don't have them yet. But now when you start here to go for the design, which means item 3, 4, and 5, now we're going to say now reduction is going to be taking place. It says here in item 3, provide the design ultimate load. Now this is going to be W ultimate. Moment and shear, which means ultimate moment, ultimate shear. For the composite W16 by 31, running between grid lines P and Q. Here is P and Q. So I'm talking about one of these beams. Any one of these beams, right? Like this beam, for example. The span is 33 feet. And the width, 28.3 inches divided by 3, tributary width. And based on this, you can do life load reduction, right? And then you can do W ultimate, you can do the design moment, which means M sub U, and then also the design shear, V sub U. So we're good with this, item number 3. Okay. What do you do after this? It says here, provide the structural design of the full composite W16 by 31. You guys, you have done composite beam design before, so nothing here is new. But you're going to be doing an actual beam design. Determine if W16 by 31 is the most economic beam to be used in this location. Consider construction life load and camber as needed. Now the question is, what construction life load would you use? And is construction life load in the code? I'm going to say no, it's not in the code. But in this case, for construction life load, I'm just going to be using here 20 PSF. How do I know it? Because I have seen it before. It is from experience. Item number 5, it says provide the structural design of the full composite W21 by 44. This is going to be a girder running on grid line P between grid lines 31 and 32. P 31 and 32. Let's give you this beam. This beam, they are all simply supported. There is no continuity. So no one would think that we need to design the entire beam here. No. When it comes now to tributary width, for this one here, for this beam, is going to be 1/2 of the way from here, right, between the other two beams to here. So this distance from here to there is going to be tributary width for this beam, or for this girder, if you like. Now, how about the metal deck direction? Where is the fluid direction or the rep direction? You can say now the metal deck is running this way. You see this D1, this is going to be the metal deck designation. It's running in this direction. So for this beam, the reps are running this way. So the reps is going to be perpendicular to the beam. For this girder, reps is going to be parallel to this girder. Now, any questions on the project information provided so far before we go back to our slide set?
Professor, can you
Yes.
go back to question number 1?
Yes.
So like how like we can do like the load design, load criteria for like the internal cover and surrounding the elevator.
You don't. I'm asking you to do the standard load criteria for here. Why? Because you're going to be using it to design this beam and this beam. So I don't want you to work on this. Don't waste your time on it. Just do the design criteria needed as dead load and live load that you're going to be using for this 2-element design.
Okay.
Good question. Thank you for asking about this.
Professor, I have a question about the girdle.
About the girdle,
So,
yes.
yeah. So when I take the maximum moment, so since they're like two like perpendicular beams on top
Yes.
of the girdle, is it gonna change the moment equation, or
Yes.
is it because is it a composite body? There's
It is
like
going to change it.
okay,
It
so it's
is
gonna
going to
be
change it.
2-point loads instead of a uniform load.
Yes, you're going to have 2-point loads, but don't forget that you're going to have a point load coming from this beam, another point load coming from this beam, right? It's going to be like this. Does it make sense?
Yeah, thank you.
So you need to do the reaction from each side, the reaction in terms of dead load and live load, right? And then you need to design them or put them this way to be able to work on this girder design and mount.
Okay, thank you.
No problem. Any other questions?
What's
Yes.
the width of the concrete in that case? Which
Oh,
one
the
we
width of
use?
the concrete?
Yeah.
As I said, it's going to be half the way from here and half the way from here. So let's see what does mean by half the way. Which means that you take here 3 feet, divide this by 2. How much is that? 16.5 feet. Am I correct? From one side? Can you help me with this? You just asked the question, right? So help me with it. How about the span from here to here? How much is this?
That's 1410.
The span is only 1410.
Well,
The
which
beam
area
is
are we looking
spanned
at?
from here to here, right? So how much is
By
this?
the way, that's 28 feet 20 inches. So that's 29.8.
Yeah. And how much is 1/2 of it? Can you help with this?
Half of it is 14 feet 10 inches.
Okay. I'll let you guys take care of it. You can calculate out, but at least you have it here and you have it recorded, so you can go back to it and then you can do your analysis yourself. This doesn't mean 29 feet minus 10 inches. It just means 29 feet and 10 inches. And this is a standard format that we write it. So what you need to do, you take the half of this distributor width, you take the 16.5 plus the other number from here, and this gives you the flange width. But you have some other numbers to control it, which is 1/4 of the span. So you're going to be taking these two numbers, you add them, compare them with 1/4 of the 20 feet, 8 and 3 inches, which is going to be about 7, let's say 7 feet, roughly, let's say 7 feet. Good?
Professor?
Yes.
When we calculate the ultimate loads, are we neglecting the self-weight of the steel beams?
No, the steel beam needs to be included.
Okay.
So when you do the concrete, when you do the load criteria, you need also say steel framing when you do items 1 and 2. But when it comes to here to this design ultimate load moment and shear for this beam, in this case, what do you need to do? You need to include the weight of the steel beam. When you do the other beam, the 21/44, you need to include the weight of this W21/44. So when you do the design of this W16/31, do not add the weight of the 21/44 because this beam here supports this beam, but this beam here does not support this beam.
Yes. Okay. Thank you.
So my advice to you guys, don't wait for Friday to start work on this or Saturday. By that time, you're gonna have questions. And as I mentioned before, you'll be sending me emails over the weekend. If I'm available, I'm gonna be able to respond. If not, you're gonna have a deadline to submit this. So please work on this, start from this evening and ask me by Wednesday. If you have any questions tomorrow at the office hour, please come in and ask me any questions you want. Is this clear to everyone here? So do not expect that I'm gonna be available during the weekend. Some cases I am, other cases I'm not. So just want to be sure that we're on the same page here.
Sir, when do we have to submit that one?
Sunday. End of Sunday.
Okay.
All right. Now we'd like to continue here with composite members. I'd like to
Sir,
see.
just one more question.
Yes.
How do we calculate the camber value?
We're not there yet, but we're going to be coming to it here. You need to figure out deflection, and as I said, it's almost the same as dead load deflection.
Okay.
So we're going to figure out how much is the dead load deflection, and say that camber is going to be almost the same, or maybe 90% of the dead load deflection. Some people would say I'd like to keep it as 75% of deflection. So we're going to get there. When we get there, I'm going to explain it. All right. So we're moving here in steps. So now I need to figure out number of Nelson studs. Now you understand when you apply loading, any loading like this uniform load, and maybe at certain point you're gonna have the maximum moment here. It means that you're gonna have a zero shear here. It means that one half is gonna be exposed to a shear, and this shear is gonna be different from one point to another point. The same thing also is gonna be in this location. So when you have the shear that you calc out is going to be called here vertical shear. You're going to have another component which is going to be coming in the horizontal direction. If you recall in the past, in the strength of materials, we used to have this two wooden beams that you put on top of each other. You guys remember this problem? That you put two wooden beams and you don't stable them or you don't screw them to each other. There's no connection or whatsoever. And then you start to apply some loads. And each one of them is going to be deflected separate from the other one. Anyone recall this problem?
No,
Yes?
sir.
No?
No, I don't.
Okay. Imagine if you have here two beams. Here's one of them, and here's the other one. Simply supported. So one support is here, and here's the other support. You put some loads from the top. Both of them is going to deflect. I guess everybody agrees on this. So when they deflect, you have here 2 points that you started with. You're going to say, this is going to be the top beam. I'm going to call the top beam, and this is going to be the bottom beam. Before you start to apply any loads, these 2 points are touching each other, right? Once you start to apply some loads, this beam here is going to deflect. Both of them is going to deflect at the same time. Now I have here 2 points. I'm going to be calling this point here to be point 1, which is the top. I'm going to call it here. This is going to be point 1. And this is going to be exactly the same point, the point which is right below it. I'm going to call it here point 2. So I'm going to put it here. I'm going to call this here point 2, right? So for you guys, what is point 1 and what's point 2? I'm going to say before we start to loading, what's going to happen before we start to apply the vertical loading, this point is touching the point which is right below it. So point 1 and 2 is touching each other, right? Now I want you here to tell me what's going to happen when you apply some loading. Do you think that point 1 and point 2 is going to be moving laterally away from each other? Yes?
Depending where the loading is placed, possibly, or
The loading is going to be from the top. You're going to have a bunch of loads from here.
okay.
So when they deflect, what's going to happen? Do you think that point 1 and 2 is going to be moving vertically because they're right above the support?
No, they are gonna have some bending, but their bending will not be the same as well. So point 1 and 2
Well,
will move away from each other.
So the bending here is going to be equal to 0, right? Because this is right above the support. And we know that they're not going to be moving vertically. But for me, I have a feeling that point 1 is going to be moving laterally away from point 2. Can anyone help me with this? You guys, have you seen this before or discuss it or no? This is something completely new to you.
Is this sort of like lateral torsional buckling?
It's going to be sliding, right?
Yeah. So what is going to be causing this sliding?
Deflection.
The bending in the middle of the beams.
Because you have lateral shear, correct? Am I correct? I'm just looking here for some old slides, previous lectures. Just bear with me for a second. Shear and beams. It's all about more circle. Anyways, so when this beam here is going to be deflecting downwards, right? Let's say it's going to be coming this way. It's going to be very tough to make it work here. Anyways, when both of these beams is going to deflect in the middle of it, this point, number 2, is going to be pushed this way. So all of a sudden, you see that this beam here is moving like this. This point is moving this way, and this point is going to be moving outwards. So this point here is going to be moving outwards. This point here is going to be moving inwards. In order for us to make these two beams to work as one unit, we need to provide some connection, vertical connection, to prevent the shear between the two surfaces. And in our case here, when we have concrete and steel, not two wooden beams, we need to provide these shear connectors. Now, the point of zero shear is going to be right in the middle, which means you're going to have a shear flow that starts from this point here, which means a point of zero shear all the way to each support. Exactly what we have here. Point of maximum moment is going to be point of zero shear. Back in the statics and mechanics of materials, you guys have learned that you're going to have a shear flow that goes from the point of zero shear all the way to the support, which means a point of maximum shear. And this is what we call here shear flow. Now, this horizontal shear is going to be equal to the compression of the concrete or the tension in the steel, whichever is smaller. So the smaller of the two, which means the C value, the compression of the concrete that we have done in the previous lecture, we're going to be taking this C, which is a smaller of 0.85 F prime C times B times A versus AS times Fy, and call this to be the shear between the support to the point of zero shear. So this V prime that we're going to be using is going to be the smallest of AS times Fy or 0.85 F prime C times AC. So this V prime is going to be the compression of the concrete, because this compression of the concrete, you need to transfer it back to the steel. So you need to have enough studs to resist this minimum compression force, which is the C. This number of studs here is going to be equal to this compression force, which V prime divided by how much each one of this mechanical connector or neutral stud is able to take. For example, if I tell you here from this point to that point, just quick numerical example here. I have total shear, I'm gonna say here compression, which is the same as V prime. Let's say it's gonna be equal to 500 kips. I did my analysis, then this is equal to here to 500 kips. I'm gonna go there and pick one of these Nelson studs. Each stud is gonna be taken, which means this is now the capacity of the stud, right? It's gonna be able to take 100 kips. Now, how many studs you need? I have total shear from here to there of 500 kips. And each stud is gonna be taking 10 kips. Let's say number of studs equals 500 divided by 10. I need 50 studs. Does it make sense or no?
Unit for QN is kips per stud, right?
This QN is gonna be kips. How many kips each one of the studs is gonna be able to resist?
Thank you.
So instead of coming up with number of studs from the point of zero shear or maximum moment to the support is gonna be equal to 50 studs, which means this force here, the 500 kips, needs to be transferred from here to there. We're gonna have another 500 kips needs to be transferred from here to there. Therefore, I need here 50 studs. I'm gonna put them right here. How about in this side? So I need the same thing, which means I need here a total of 100 studs, not just 50. You don't just take the force 500, which is a V prime or the compression force, divided by 10, and for that you're gonna say, now I need it for the whole thing. So this N1 is gonna be equal to V prime divided by Qn. And this V prime is gonna be equal to the compression force that we just considered in our analysis in the previous lecture. And this is exactly what you have used in solving homework 4. So this N1, you're gonna repeat it. It says here N1 and also N1. So you need to have here 50 studs and also here you have 50 studs. Any questions? You're good? All right. Now, I threw here this number, I said 10 kips for a stud. But now we'd like to see a way or maybe a table to help us with determining this Q sub n. What the code says here in this equation I8-1, it says Qn is going to be equal to the following, and then give it this to me in one equation. But actually, this is like two equations. Here's the first one, and here's the second one. You have here two equations. It says Qn equals to 0.5 of the cross-section area of the stud, square root of F prime C times EC, and this is going to be all in case sign. Also, it tells you that Q sub n is going to be equal to some parameter, something called R sub G, a factor, times R sub P, times the cross-section area of the same stud, times F sub U, which is ultimate strength of the stud itself. And then it says, take the smaller of both of these two. You're going to be taking the smaller of the two. Meaning, you need to run both of these two equations and then pick the smaller of these two values. Let's see here these items, the symbols used. ASA is giving the cross-section area of the stud, is giving inches square. Can I just choose any stud size? You can say no. We have certain studs, and very soon you're going to see some tables with the available stud size. F prime C concrete strength is going to be in case psi in this case. E sub C, I guess went through this and you guys know how to calculate that. It's going to be this E sub C, well, the modulus elasticity also in case psi. R sub G is going to be the group effect. So this is going to be like a reduction factor. If you have lots of them, lots of studs that you put in the same location, you're going to have some reduction. So it says here R sub G is going to be coefficient to account for group effect. Generally speaking, this R sub G and R sub P is going to be like a reduction factor, which means maximum value is going to be equal to 1 if there is no reduction. If you have some reduction, you're going to see a lower value than 1. R sub P is going to be based on the position. Where do you put the stud relative to the deck? We're going to be looking at this. And then it gives you a couple of values for R sub G and R sub P. Ultimate tensile strength for a stud, just so you guys know, it's going to be 65 KSI. Constant. Just a constant value that we have for studs. Now let's see here the following chart. This also is going to be a table taken from the AIC for the RG and R sub P values. It says here if no decking, like metal deck. So this here means no metal deck. So concrete deck is going to be there. So I'm going to put next to it no metal deck in this category. It says if there is no metal deck like our previous examples, but this is going to be unlike our project and homework. So in this case, you have done RG of 1, which means no reduction, and R sub P of 0.75. So, okay, simple. If the deck is parallel to the steel shape or the steel beam, what does it mean deck is parallel to the steel beam? When do you think this is going to happen? Is this in beams or girders?
Girders.
So I'm going to write here girders. About this group here, it says decking oriented perpendicular to the steel shape. You say, okay, this means it's going to be for beams. Good. And then there's some definition here at the bottom. It says when you have WR divided by HR is going to be more than or equal to 1.5. What's going to happen? Here is your RG and here's your RP. If this going to be less, 0.85 and 0.75. So what is WR and HR? I have them right here. It says the nominal rib height, and it's giving the average width. Let me move here forward one slide to see what this mean by WR and HR. Here is WR. It's give you from this point to this point. Where is HR? This is going to be HR. So HR is going to be the depth of the metal deck only. So in this case, I'm going to say when I have W3 is going to be equal to 3 inches. So, okay. How about WR? Usually, how much is this? You say the distance from here to there is like 12 inches. So most likely this WR is going to be equal to 6 inches. Now I have an idea about definition of WR and HR. You can open the metal deck of your choice and look at this HR and WR values. So, okay. Most likely, WR to HR is going to be more than or equal to 1.5. Why? Because WR is going to be 6 inches and HR is going to be either 3 inches or 2 inches, which means you should be able to satisfy this condition. You're going to end up with RG of 1 and RP of 0.75 for girders. So good. How about for beams? I have here a few cases. It says number of steel headed stud anchors occupying the same decking rep. If you just have one, it's going to be 1 and 0.6. If you have two, so I'm wondering what does it mean by that? What does it mean occupying the same deck? So I'm going to go back here. I'm going to be opening our slides, looking back at the previous slide set. Looking at slide set 5, which is this one here. You can go back to the Verco catalog. You see this? You have only one stud. Here you have two studs. So you have here 2 rows of stud. Look at this. Here you have 2. Sometimes you have 1, or you may have 2, or you may have 3. So I'm going to be looking here at this is only, it's going to be 1. You see this? It's going to be only 1 stud. This is going to be again 2 studs. I guess now I understand what this mean by 1 and 2 and 3, and here's some reduction factors based on this value. But look at this value here in item B, because you see this is going to be 0.6, right? I don't like this 0.6. I'd like to keep it as 0.75 as much as I can. So it says here for B, it says this value may be increased to 0.75 when this number here, E of the mid height, is more than 2 inches. I'm wondering, what is this E mid height is going to be more than 2 inches? So we're going to go here to the next slide, this one. Here is E of mid height. It says when it's going to be more than 2 inches. Most likely we're going to be using W3 or W2. And of course, this is going to be higher than this, than HR, which means this condition here would usually apply, this B. And in this case, this is going to be 1 and this is going to be 0.75. So in most cases, if there is no metal deck, I'm going to be using this. If I have girder, I'm going to be using this. If I have beams, I'm using either this or this. But in this case, this factor is going to be 0.75. So most likely, I'm going to be using this to be 0.75. Any questions? Okay.
For the Professor, sorry, when it says no decking, that means no steel decking, right? It's just like a concrete on a steel beam.
Yes,
Or
it's going to be
concrete.
concrete on a steel beam, and you're going to have the metal deck like what you have seen in this case. So this is going to be concrete, and here's the metal deck. It's going to be this thin black line, and here's the steel beam. This here, when the deck is going to be parallel to the beam, it's going to happen in girders. You write this down here. And most likely this is going to happen in beams.
Professor, for girders, what's the thickness of concrete that we consider?
Here?
Yeah.
Are you talking about the project?
No, just in general.
In general, you'd like to start with 3¼ inch lightweight concrete if possible.
Okay, so are we considering like above the steel deckway jogs or right at the top of the beam?
The 3¼ is going to be whatever above this point.
Oh, okay.
So when I say here 3¼ above W2, this is the way that we say it. Or we say W3 with 3¼ it means that I'm going to here. Let me show you which one. You see this here, it says W3 with 2½ inch. Where's the 2½ inch? Do you see it? Do you see the term here, 2½ inch? No, but it says here 5½. But everybody would call this, he's gonna say W3 with 2½ inch concrete on the top of it. Meaning that from here to there is gonna be 3 inches, and the concrete above the deck, above this, which means the thinnest part of the concrete slab, is gonna be 2½. This is a common one. Let me show it to you. I put all the common ones here in this slide set, so that if you are thinking which way should I go or which deck should I pick, what concrete thickness, you're gonna be looking at this and say, this give you the common ones. If you open the Verco catalog, you're gonna see lots of other deck designation and combinations, right? But I put here the common combinations here for you. So most likely, you're gonna be going with this. That's why I put here this red box, 6¼ inch above W3. So the way I'm saying it is kind of confusing because we used to say 3¼ inch. So you cannot really say 6¼ right? It's gonna be a 3¼ inch above the metal deck. So you say 3¼ inch concrete deck with W3. Or like in this combination here, I'm gonna say this is gonna be W3, right? Metal deck with 4½ inch. Why 4½ inch? Because you have 4½ inch above the W3 to give you a total of 7½, which means from here to there, this distance is give you how much here? 4½. And this distance from here to there, this is give you W3. Is give you 3 inches. Total of 7½. So now we have an idea about our equation, the
So,
use of it.
sir, in condition 1, we don't have any work with deck, right?
Say it again about Verco deck. What did you say?
in condition 1 where it says no decking. We don't have any work with deck, right?
Yeah, when there is no metal deck, no decking, it means no metal deck. It's gonna be just concrete slab. Like also what we have in this problem. If you give me a second, let me go back to this problem. Like in here, for example, right? Look at this. Do you have here any metal deck? No, you have 4.5 inch, right, attached to the steel beam. There is no metal deck. In this case, they're gonna have here some formwork and they're gonna put the concrete to be flush with the steel beam. All right. We have this nice table taken from the code. It just gives you directly Q sub n. This table here is the old table. So these values, you're gonna see them, they look okay, but these values are incorrect. You guys have the steel book in you? Can you double check them, please? And here's what happened. You see these values that I put right there? This can be the same table, table 3-21. I'm gonna go back here for quick. Table 3-21. You see this value here? 653, 11.6, 18.1, 26.1. Now the new table, instead of these numbers, these are the numbers now that we have. 538, 957, and so forth. And this gonna be 26.1. So instead of 21, 26.1, now we have 21.5. So now it's different. I'll show you why the difference and what happened. So I'm gonna go back here. I'm gonna say, in this nice table, table 3-21, in the steel manual, you're gonna say here, it says F sub U is gonna be equal to 65 KSI. What is F sub U? I'm gonna go back here to my equations, give you this F sub U, give you the 65 KSI. What is good about this table here, it shows you the available stud diameter, 3/8, 1/2, 5/8, and 3/4. This gives you the available stud that you'd like to use. In actual practice, usually this gives you the one that you need to work with, the 3/4 inch. No one would use a 5/8 or the 1/2 inch. We don't really use it. We just go to the 3/4 inch, especially when you know that there is no big difference in price between the 5/8 and 3/4 inch. So you're gonna say, why don't I just go ahead and use the 3/4? Makes sense. It says here, here's where you have no deck, no metal deck. And here's we have the deck is gonna be parallel. Next page, when the deck is perpendicular. So you can see this is good. This is actually the same as this table here, right? No deck, deck oriented parallel, which means girders, and then deck is gonna be perpendicular, which means beams. And say this is exactly what I have. No deck, girders, and then beams. So, okay, good. Stud diameter, concrete, nominal concrete, which means this is gonna be normal weight concrete versus lightweight concrete. Here's the unit weight, like gamma sub C, 145 PCF, 110, two different concrete strength values. If you have the concrete strength of 3 KSI versus 4 KSI, and based on this, you can pick Q in directly from the table. This table does not include concrete strength with 3.5 KSI, but if you have, let's say, if you have 3.5 KSI concrete, in this case, don't do the average, and instead go ahead and use these two equations. Because the relationship is not that linear. Because look at this equation, square root of F prime C times EC. There is no linear here relationship. So I just go back to this equation and use it. It's okay. It's good that we have this table, should be able to help us out. So in the previous manual, that was the exact values presented to you guys. So the reason that I left this there, because I want you here to know the difference between the old code and the new code. In the old steel manual, the 14th edition, that with the numbers. In the 15th, they changed these numbers. Tell you the reason. Let's do here one example. This example is about the previous beam that we have done at the end of last lecture. We have this W18 by 35. Here's the steel. You have 4 KSI for the slab, 4.5 inch. The span is 30 feet, and the compression in the concrete was 515 kips. So Now I don't really need to start the whole example here from scratch. So I just started here from the point that I need, because all what I need to do is to find out the number of studs that I need to put there. If you like, go back, here is the problem that we was working on. 515 kips with a compression force. I have 4,000 concrete. So here's the force, 515 kips, simply supported. I need to put Nelson studs to connect between the concrete and the steel beam. And I'm looking for full composite action, which means I need to transfer this 515 kips from the point of maximum moment to the point of maximum shear from each side. So what I'm trying to do here, I'm trying to use this equation. At certain point, I'm going to be comparing it with the table values. When you look at this equation here, it says 0.5 of ASA. ASA is going to be the cross-section area of the stud. We decide here to use a stud of 1/2 inch, and here's the cross-section area. It's roughly 0.2 square inches for one stud, 1/2 inch. When you do here EC, is going to be equal to gamma of the concrete to the 1.5 square root of F prime C. I have this value here. Said fine. Q sub n is going to be given by these two equations. And of course, can be taken the smallest of the two. If you try here the first equation, which is based on the concrete strength, 0.5 times 0.2 times the square root of 4 times 3492 is going to be 11.6 kips. So this here pays on the first equation. Based on the second equation, when I try this number, now I have concrete slab, no decking, no metal deck. And for the group action, I have it as 1. For R sub P is going to be 0.75 times the cross-section area times F sub U of 65 kSi. I have 9.57 kips. Now, which number to pick? Which one controls? I'm going to say the number controls is going to be the smallest of the two. I'm going to be using here 9.57. Is it fine? Now I have this answer. Now I have.
In ASA, where did you get 0.5?
What?
In ASA value calculation, where did you get 0.5 from?
This one
0.5 square. Yes, sir.
We picked 1/2 inch. That was the choice. We picked 1/2 inch stud.
Okay.
That was a choice. That we're going to be working with 1/2 inch stud. Here are the stud size. You can 1/2 inch, 5/8, 3/4, or 3/8 inch. So in this case, went with 1/2 inch.
So we can choose any of those studs.
Yes, unless it is indicated to you.
Okay.
And as I said, most likely, if you are practicing, actual practice, please remember this. It's going to be 3/4 inch. So don't just pick anything. If you are working maybe with the senior engineer, ask him which size to use in the real application. So I did here these two equations. One of the equations, which is based on the concrete strength, it gives me here 11.6. The other one gives me here 957. So I said I'm going to be picking here the lowest of the two. So it's fine. I'm just skipped here one slide. I'd like just to talk about this. I'm going to say here's the old code and here's the values based on the new code. The old code says it's going to be 11.6 kips. The new code now reflects the other equation, the 9.57, which means that was a mistake in the old code. In the old steel manual, the 14th edition, that was an issue. They show it as 11.6. Now they show it as 9.57, and they just put it here in the same order. Now, let me go back here, 2 slides. Look at these two equations. It seems in the old steel manual, they used to refer to only this equation. And this equation was not considered. You see 11.6, 957. Let me move forward. Here's 11.6 for 1/2 inch. Should have been 9.57. Now the new code includes this 9.57. All right. So what needs to be done? I'm going to say now number of studs. How many studs do you want to add? we're going to say N1, which means 1/2 of the beam will be taken the 515 compression force divided by 9.57, which is how many kips each one of the studs is going to be taken as shear force, the strength. And it says here 53.8. So in this case, I'm going to be using 54. If you have 54 and 1/2, it means in both sides you're going to have a total of 108. Just take this multiplied by 2. Any questions? If you like, you can sign out. Just type your name and leave. If you have any questions, stay with us, please.
Professor, in the project, will we be safe to assume 3/4 for the diameter?
Yes,
of the stud?
3/4 inch. Yes, Nelson size is going to be 3/4 inch.
Okay, thank you.
No problem.
Professor,
Yes.
if we use the old code, the one I have, is it there gonna be any problem with it?
Try to update it, update some of these values. If you have any friends, anyone has a newer version, try to do the latest values from the newer version.
Okay.
And you can mark it, you can do it in a pencil next to the old information, you know?
I'll try. Thank you.
No problem.